Hello, what's up, people? Today I'm gonna show you how to do logistic regression in Python. Okay, this is part of the series Machine Learning from Scratch. This is episode 2, Logistic Regression. Come on, let's go. So, before getting into the code, I just want to talk about what logistic regression is and how it works. So, I have created a presentation for that because I was too lazy to write on the whiteboard. Let's start. So, ML from Scratch episode 2. Yeah, what is logistic regression? Let me just move this. Yeah, this is good. Basically, logistic regression is a machine learning method to classify data into classes. So what we're going to be talking about today is binary logistic regression. What that means is that suppose you have a set of data. Suppose there are a couple of numbers. Let's say you have the features of a cat and a dog, and you want to classify if given a set of features that if that animal is a cat or a dog. So you can use logistic regression and classify that particular set of features into either two classes, 1 or 0. We can take 1 as the dog. If it is 1, then it is the dog, or if it is 0, if it's the cat. Like that. It's just classification, binary classification. So, wait a minute. Okay, how does it work? So, in the last episode, I did a video on linear regression. If you haven't watched it, please go watch it. In that, I basically created a linear equation with randomly, generated variables, and I, did gradient descent on that to obtain the optimal weights for that particular data set. We're going to do the same thing here. Instead, we're going to form that linear equation, and since we need that output as a probability that one thing is a dog or a cat, right? What we're going to be doing is we're going to activate that. And by activating, I just mean putting that linear regression as an input to a function and getting an output which is of between the range 1 and 0, so that we can get our predicted outputs later when we finish training this model. So this is called the sigmoid function, right? Whenever you input any real number into a sigmoid function, you will get a value ranging from 1 to 0, right? So how does sigmoid work? Suppose we have the range as negative infinity to positive infinity, and here we have the sigmoid function. Now the thing is that infinity is not actually a number, so I can't represent that and put it into a function. However, I can limit the function to infinity. See, what I have done here is that I have taken the limit of x tends to infinity for the function, and what I get is that, see, we have 1 plus e raised to negative x, which is basically 1 plus 1 by e raised to x. And while limiting by infinity, we have learned that during a fraction, if a fraction is taken the limit to infinity, what happens is that if the denominator of that fraction gets really large, we can approximate the value of that as 0. Now we can see that 1 plus 1 by e raised to x, where 1 by e raised to x gets really larger. The e raised to x part gets really larger. And what we result in is a fraction which has a value really tiny, and we can approximate that to 1. So we have, like that, we have the 1 if infinity is inputted, right? Can we say inputted? I don't know. Yeah, I'm sorry for my grammar. Alright. Then we have limit of x tends to negative infinity, and we do the same thing, but however we see that in here, I forgot to put that infinity in place of x, but you get it, right? So what we're doing here is that in this, e raised to negative of negative infinity becomes e raised to x tends to infinity, and as I said before, if the denominator gets really large, we can approximate it to 0. So here we can see that it becomes 0. That is how sigmoid takes an input and presents it between the values of 1 and 0. Next we have the loss function, binary cross entropy. I'm gonna get into that, but you may have a question. why can't we use mean squared error? I'll explain that in 1 second. So why do we use binary cross entropy? In the logarithm function, log function, there is a peculiarity. See, once you input a value which is really close to 0 in a log function, we get a large negative output. And if we input a value really close to 1, we get a small negative output, probably like negative 0.0015 or something. And how does this fact help us? If you notice in this equation that suppose this yi, there are labels, right? So it can either be 1 or 0. And if it is 1, notice that the second side gets cancelled. If it is 0, the first side gets cancelled. So we only have to deal with one equation according to class, either 1 or 0. Now I have separated these two equations, and as you can see, negative y log p is the equation if our label is 1. So what happens is, as I said before, we want our output, if the label is 1, we want our model to predict 1, right? And what happens here is that, as I said before, log of values closer to 0 produces a negative output. If that particular p is a predicted value, right, after we activate it through the sigmoid, and if suppose p is really small, then we will have a really large negative number as the output. And since y is 1, we don't have to multiply it by anything. What is that property? I'm just really, this is unscripted, by the way, so it gets a little bit awkward. As I was saying, right, we get a really large negative number, and this negative sign here makes it a really large positive number, which we get as the error, right? So that is awesome. We get an error which is a really large positive number if the predicted value is really small. If the predicted value is really close to 1, then we get a small positive number as the error. The same thing happens in the second equation. If you can see that this 1 minus y part simplifies to 1, because this equation, we only have to consider this when the label is 0. And in the log part, what happens is that we want, whenever our label is 0, we want our prediction to be 0 as well. Here, the interesting thing is that whenever our prediction is closer to 0, due to the 1 minus p, it becomes closer to 1. And the same effect, as we discussed in the first equation, the same effect happens in the second equation. And if the predicted value gets closer to 1, it becomes a value close to 0 due to the 1 minus p, and that induces a large error. So that is how binary cross entropy provides like a really large error. Now why can't we use mean squared error? See, mean squared error provides a maximum error of 1 no matter what. A maximum of error of 1. For example, if you have a class of 1 and a predicted of 0, you only get 1, which is the maximum, which is not enough for optimizing with gradient descent. And I could get deep into this, but we don't have time for this that in this episode. And so I'm gonna link down in my description there are going to be 2 links, one discussing about cross entropy in a visualized way, which I found really interesting, and another one about why mean squared error can't be used in logistic regression. So now, man, we're getting into the derivatives. Yeah, so we have to do a gradient descent, obviously. So here I'm just showing how to derivate with respect to the weight variable, because we find in the final steps we get a generalized form, and this is just basic differentiation. We split that equation into 2 parts, as I said before, and we derivate. I hope you look through these notes, and if you have any doubts, please comment on the comment section. Yeah, I'll just go through these notes briefly, right? So we have negative y log p, then we take negative y outside and take the derivative of log p. P I have already denoted here, and anything inside a log must be the derivative of that must be its reciprocal. So we flip that inside equation, and we take the derivative of 1 by 1 plus e raised to negative wx plus b. We use the chain rule, we take the derivative, we get to the simplified expression. In this as well, we follow the same thing, but instead here, because it is log 1 minus 1 by 1 plus e raised to negative wx plus b, we cross multiply and we get e raised to negative wx plus by 1 plus e raised to negative wx plus b as the inner function, the function inside the log, the expression inside the log, and we flip that and we get this particular expression and this chain rule, and at last we get this expression. Let me just this expression 1 minus y into x by 1 plus e raised to negative wx plus b minus y x by 1 plus e raised to negative wx plus b into e raised to negative wx plus b, and we can take x by 1 plus e raised to negative wx plus b outside, and when we take that outside we get 1 minus y into e raised to negative wx plus b, and we can group these y's together and take the y outside, we get this. And when we multiply that by 1 plus e raised to negative wx plus b, we get a familiar thing. It is just x into sigmoid, the activation, the prediction, minus the actual output. And if you check, we can generalize this to a higher level. We can say that coefficient of what needs to be derivated into the prediction minus y. So for example, if we had to take the derivative of the bias, we would just need to say p minus y, because the coefficient of the bias is 1. So please take a look through these notes. I know they are not complete, they are not that high of quality, but I'm going to leave the link. They are going to be in my GitHub repository. Yes. So our presentation is over. Now it's time to code. Yeah, come on, let's go. I have already opened up Sublime, right? Yeah, so first of all, I'm gonna import NumPy because I need NumPy for those logs and exponential. I'm gonna import NumPy and I'm gonna initialize the dataset. Dataset is gonna be, let's take a simple program. Suppose a number becomes greater than 5. We classify it as 1. If it is lesser, we classify it as 0. Simple dataset. So I'm gonna say 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 itself is going to be in the 1 category. So yeah, so y is going to be like 0 0 0 1 1 1 1 1 1. Yeah. So now I have to initialize random variable. So I'm going to use the random library from Python. not random. Yeah, it's just random. And w is going to be random initializing random weights, and bias is going to be random. Yeah. So now I have to loop through it. So I'm going to define a function def train, and train I'm going to input x, y, w, b. And also if you have watched my last video, you know that every machine learning model, not every but most of them related to deep learning, most of the models related to deep learning need a parameter called the learning rate. Basically what happens when we take the gradient descent is that we're slowly optimizing that weight value to learn that function a little better, to change the weight value in such a way that the error is lower, right? So we have a learning rate variable which tells our model on how fast we need to move so that we can find the optimal weight value, weight bias value, whatever. And if you don't know about that, please go and watch the first video. I think I have explained it there. So yeah, please watch it. Also, I will get more views. Yeah, that was awkward. Yeah, let's go. Yeah, as I was saying, I have defined the train function. Yes, come on. Now I'm gonna go through a for loop for I in range. As I said before, in the last video we had iterations, right? So I have to define iterations and learning rate. So I'm gonna say 1,000 iterations and learning rate of, let's say I'm just gonna say 0.1. Let's say 0.1. So for I in range, length no iterations, right? Iterations, and for j in range, length of the training data, right? Now what we're gonna be doing is, first we're gonna make a prediction, then we're gonna calculate the error, then we're gonna update those values using gradient descent. Yes, so we have three functions to build. Yes, so first is the prediction function, prediction, and that will be the x value comma y value w. No, we don't need a y value, by the way. We just need weight and bias, and we can say the linear prediction will be w into x plus b, and we will have to activate it. So return 1 by 1 plus numpy dot x, that's the exponential function, numpy dot x negative linear. Okay, so we have the prediction ready. Now I'm gonna say predicted value is gonna be prediction, and the first element of the x data set, and we have w and b, right? We have the prediction ready. Now next thing is calculating the error, right? So let's say error, and let's say a function called, let's say, cross entropy. In cross entropy, we're gonna give the element of the y data set and the predicted value, right? Element of the y data set and the predicted value. So we have to initialize def cross entropy, def cross entropy, def cross entropy y and predicted. And what I'm gonna be doing here is, we have to what is that function? I forgot. It is actually let's see, come on, y into log of prediction plus 1 minus y into log of 1 minus prediction. All right, it's coded out. Yes, so I'm gonna say return negative y into numpy dot log of predicted plus 1 minus y into numpy dot log of 1 minus predicted. And we're gonna return that. Now I'm not gonna be calculating error over epochs, just for simplicity's sake. Doing so will probably improve the model, but when we are coding like this, it doesn't matter really, because this is just a demonstration. I want you to apply this model and make better things, right? Make better things out of it, make things that people can use, that are applicable, right? This is just a demonstration, remember that. We have calculated the error. Now it's time to back propagate. Yes, so I'm gonna call back propagate, and I'm gonna say w and b return back propagate. That is the spelling, I hope. Yes, so we have error and predicted and w and b, right? So we have mouse cursor. It is really naughty. Back propagate, right? Back propagate. Yes. See, we have the error and the predicted and w and b. Now we calculated the back propagated value. That came up to be what, x into p minus y, I guess. The last derivation that we got, x minus, that is coefficient into the prediction minus the y value. So I'm gonna be saying w, the minus is equal to what, the coefficient was x. I have to put x as well, so xi, right? I have to put xi as well. Yes. Now we also have to, no, I don't need the error actually. Why am I doing this? I am messing this up, right? So I need the x value, the y value, which is the actual output, and the predicted. Yes. Now this has change xy, right? So is equal to x into predicted minus y. B minus is equal to just predicted minus y, and I will return w and b. And here I'm gonna print the the error and which data is it looking at that specific moment. So I'm gonna say string of j, and I'm gonna have this little colon for fun. I don't know. And never mind, I don't need a colon. So string of, I'm gonna copy this command, I'm gonna put this here, and we have the string of error. String of error, which is added to this. No, this is all messed. I'm messing this up. All right. Here error, and we have string of error. That is good. Now I'm gonna create a string to print the iterations, right? Iterations, again, colon. I love a colon when I can put something there. Never mind. Oh, I indexed it wrong. It should be j. We would have to debug it. So that is actually j, it's not I. So then I'm gonna print the after this I'm gonna print the final weight and bias values. Nice. So let's try it. Let's train it. Train x, y, w, and b. Let's see. I'm gonna go to the terminal and run it. I used plus. We're getting this not a number error, which is basically when the error is like really small or something, we get that not a number. Let's just test it, right? Let's test our final weight value. So I'm gonna open up the Python thing, and I'm gonna initialize the variables here. Copy this, paste, and b is equal to -46. And paste it. I'm gonna say prediction is equal to 1 over. Let me just import numpy. Importing numpy. I messed up the spelling of import. Holy crap! This is funny. Have a good laugh. Laughing is actually pretty good. Not as good as me getting off topic. So we have negative w into, let's give it a number. Let's say 3. Let's go 3. 3 plus bias. We have one more thing, and that is good. Let's print the prediction. Oh, I have to round the prediction. Okay, let me just round the prediction, and that is 0. That is good. It is actually working. Let me just change the prediction and let it set to something like 14. So it should predict a 1, right? Let's see. And I'm gonna say round of prediction. Yes, that is a 1. That is good. So that is basically our machine learning model. This is the basic principle behind it. As always, thanks for watching. Please, if you have any comments, if you have any suggestion, if you have any criticism, please comment down below. And I'm posting the link for the code under the description, and for those not so good lecture notes, kind of. So I'm gonna post those down in the description. That's it for now. See you guys.